Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. In this video, we'll review some of the most often used techniques of digital signal processing in acoustics.
So let's get started. We know that analog acoustic data that we measure using microphones, it's ultimately digitized when it's processed in computers. And there are many common digital signal processing steps that are used throughout acoustics applications. This video will familiarize us with these processes through a number of simplified examples. The first is understanding the acoustic impulse response. The impulse response of the system is a behavior induced by a brief impulse. This could be an actual brief impulse, or it could be the result of white noise or initial conditions. If we do that for this mass spring damper system, we intuitively know that we would have a ring down response, a sinusoidal oscillation superimposed with an exponential decay. The impulse response is important because it's a built-in characteristic of a system, and if we know the impulse response, we can compute any arbitrary response due to any arbitrary input. Convolution is the process we use to convolve an input with the impulse response to find the output response. The continuous convolution integral shows the impulse response h, the input x that are convolved, integrated over time to find the system response y. In discrete form that would be conducted by computers, the discrete time indicator is k, and we see the same convolution in a discrete mode, converting the integral to a sum. In block diagram form, the impulse response of the system is the block, where the input x goes into the impulse response, sending out the system response y. Let's look at some example data. We have the ring down response that we've just seen on the prior slide. This is the impulse response. The input is this period and a half sinusoid. When they are convolved, we find this final output y. When computed, convolution is the area of overlap between the input and impulse response, which means when we consider an animation of convolution, the net overlapping area is the instantaneous temporal response. So only when the period and a half sinusoidal input x crosses over the impulse response h do we see the y of t output of the system response occur. We find the impulse response for real systems using a frequency time domain transformation. We first start off with our measurements. We take an input, we measure an output, and we're interested to know the impulse response of the system through which the input passed to become an output. We first do this by converting these temporal responses to the frequency domain. It's the Fourier transform that can make this conversion happen. But specifically, we block and segment our output and input over, for instance, 1 second durations. We then window those signals, very often using a Hanning or a Hamming window. The windowed version of this 1 second output response is shown in the bottom of the schematic. Then these windowed responses are converted using a Fourier transform to the frequency domain. We then average over each block increment, for instance, the 10 blocks that occur from 0 to 10 seconds. These are ultimately the averaged frequency responses. These are plots of the amplitude, but the FFT also gives complex values denoting the phase. Then, the transfer function we find through the ratio of the output to the input frequency responses. Again, only the amplitude is shown here, but it also includes phase information using the imaginary component of the transfer function. Finally, taking the inverse Fourier transform gives us the impulse response of the system. In other words, with this input x on the left and the impulse response of the system h in the middle, that shows why we develop the output y through convolution. This process can be conducted on acoustic data as well. A microphone measures the response of a speaker that is then heard through microphones. The system that we wish to determine the impulse response for is the propagation of sound from the speaker to the microphone. And for head-mounted microphones, this is called the head-related impulse response, the HRIR. HRIRs can be pre-measured and then called through a tabulated mode in spatial audio algorithms, in a similar way that gears are chosen in a transmission map for internal combustion engine vehicles. For instance, this is used in real-time spatial audio applications. In a scene of a moving character, the mono recording that's originally acquired is convolved with incrementally changing HRIR's head-related impulse responses to create a sense of a moving sound source. So as the characters are flying in this avatar scene, various HRIRs denoting the different spatial positions of the figure in the video are convolved with the mono recordings, which, when played back on speakers, help audiences experience a sense of immersion with the scene itself. To summarize what we've learned, acoustic measurement frequency responses are straightforward to process, and they provide us an easy access to the impulse response through the transfer function. The head-related impulse response, or HRIR, it's the data that we convolve with microphone signals to create this spatial audio effect from simplified recordings.
That's it for this video. In the next video, we'll see how these digital signal processing approaches are used for active noise control.